Okay. Okay. So okay. So now this is the lecture on quantum mechanics one. Okay. So and the word quantum itself actually sounds very fancy and fascinating to most of us, because let's say if we look at today's world around, we see that almost everything is dominated by quantum idea, right? Like this is a spintronics, that is a electronics based on quantum spin ideas that gives us more dissipation free current transfer. And then there's this laser technology, which is also like an example where quantum technologies has been used. And then not nothing to mention about this quantum computation. You all like are very aware of this fact that how much quantum computers are hyped these days for its faster computation techniques. And there's this semiconductor and nanostructure, these microchips that we are using in our everyday life, that are all basically based on the quantum physics ideas. So basically, we can see that quantum is present everywhere in our life, even without most of us knowing about that. So basically, before going into the detailed or formal calculation or derivation about the topic, I think a brief history about the subject will be interesting for all of us to know. Uh, because it is interesting to know always that how a subject or how an idea appeared and how it why it appeared on the first place. So for that, let us look at a brief history of quantum evolution. So imagine yourselves in the beginning of the 20th century. All right. So 20th century means the year of 1900 and onwards. So back then, the world was basically dominated by the classical physics ideas in science. So these were the most four basically well-known topics of classical physics that were like researched at that time. That was this classical mechanics, thermodynamics, statistical mechanics, and electromagnetics. These were the pillars of science and classical physics back in year 1900 and onwards. But then, okay, so scientists had this idea that everything that was important to science, to technology, was already been discovered, and there's nothing new or important to discover after that. So if you look at the quotes of some of these scientists here that I have noted, you see that Lord Kelvin in 1900 said that there is nothing to be discovered in physics now. All that remains is more and more precise measurement. Okay, and along the same lines, this man Albert Michelson, who was the inventor of Michelson interferometer, he also said that the more important fundamental laws and facts of physical science have all been discovered. So our future discoveries must be looked for in the sixth place of decimals. So basically, all these give us the flavor that actually scientists thought that nothing new or nothing very crucial were left to explore back at that time, and we can only the best we can do was to measure more and more precise of the same thing, right? But then the irony was the quantum idea emerged. So the quantum idea emerged and it actually changed the way we used to look at the world before that. The world we looked at in the classical point of view, but then quantum idea emerged, and the man behind this idea, who first like mentioned this quantum hypothesis, quantum idea, introduced us to this term, was this man who is the godfather of quantum physics, we say, is Max Planck. Basically, this man was behind the first initial invention of quantum theory. So, this is the famous Planck's hypothesis of quantum in 1900 on blackbody radiation, which we'll discuss in more details in this lecture only. But now, initially, just have a brief idea that before quantum idea came in classical physics, we used to think that energy is basically continuous, right? And then Planck said that energy is not continuous, energy is discrete, and these discrete energy levels are defined by this formula equal to nhν, where nu is the frequency of the harmonic oscillator of the atoms of this blackbody radiator in this case, and n is different integers like 1, 2, 3, etc. And h is the famous constant known as the Planck's constant. So this was the initiation that proposed that Planck proposed that energy is not continuous, but energy is actually discrete, like discrete energy packets. Okay, and then you can see in this picture, this is there are two famous men in this picture. One is Planck himself, and other is Einstein, which we all have heard of or known of. So these are two pioneers of quantum physics. Uh, Based on the Planck's idea of quantum, later Einstein developed this idea even more further, and he discovered or explained photoelectric effect in 1905. And he confirmed that not only for black body radiation, but any light or radiation or wave actually have a particle like nature, because its energy actually comes in packets, and the size of each of the packet depends on the frequency of vibration denoted by mu. Okay, and these are some more pictures. This is the core developer group of old quantum theory that was first initiated in the beginning of 20th century. So this man is Niels Bohr, who actually gave us the atomic spectra and atomic model. This is Albert Einstein himself. This is Planck. This is Pauli. This is Heisenberg, and this is Schrodinger. So these three men, their contributions will be familiar to us once we move forward in our lectures. So for now, we can just say that they are the core developers of quantum theory, old quantum theory. And this is also a famous conference picture in Belgium 1911, which is denoted as the golden age of quantum revolution. Many of the pioneers of quantum mechanics, quantum physics ideas are sitting here. Like this is Planck, and say this is, I think, Sommerfeld. This is, I think, de Broglie. De Broglie hypothesis we'll discuss later. This is Wien. His contributions will be known to us in this class only. This is, and in this picture on the right, Einstein is there. So basically, these are the famous people that were behind this quantum idea. Okay, now it is very interesting to know that even the most brilliant minds at that time, the scientist himself, were very much uncomfortable with the idea of quantum at that time. Now, if you look at some of their quotes, like Niels Bohr, whose picture I have shown you just right now, he said that those who are not shocked when they first came across quantum theory cannot possibly have understood it. Okay. And along the same lines, Einstein has also said that I cannot accept quantum mechanics because I like to think the moon is there even if I am not looking at it. It actually represents how much counterintuitive it seemed, quantum mechanics seemed to even Einstein, who himself developed or contributed a very huge amount to the evolution of quantum mechanics. He himself was not comfortable with the idea because it actually did not come very smoothly out of our intuitions like classical did. Okay, and Richard Feynman, this man also is very famous. Most of us have must have heard of him. He also said that nobody understands quantum mechanics. Now, all these quotes I have put just for a reason that if at some point of time some of us might think that okay, we are not even like comfortable with the idea, or we cannot think of the topic by our intuition, then there's nothing to be worried about, because even these great minds also were not initially comfortable with the idea of quantum. So basically, the best we can do is that we will try to compare the ideas of quantum with classical ideas, and we'll try to connect the physics behind these calculations as much as the best of our understanding. Okay, so this is a brief comparison that I have put into so that we can distinguish how quantum is different from classical. So before we always used to do classical physics, which is basically only applicable for macroscopic systems, that is for larger bodies, like we see in everyday life. But quantum basically can deal with microscopic or subatomic bodies, like very small scale bodies are dealt with quantum. Now, quantum is a more fundamental theory because it can explain both microscopic objects, and also it can be applied to macroscopic systems as well for certain limits. Whereas classical idea is more of a special case of quantum theory because it cannot explain the microscopic objects. It can only explain the physics of the macroscopic objects. On one hand, quantum ideas are more uncertain. All we can look at is possibilities and probabilities of different events, whereas the classical ideas are predictable. They say that future can be predicted once we have complete knowledge about the system. Like classical says that energy is continuous, but quantum says that energy is not continuous. It comes in discrete wave packets, as I have mentioned earlier too. And lastly, but not the least, that classical ideas propose that waves and particles are entirely two fundamentally different ideas, whereas quantum propose that wave and particle are basically a dual nature of the same object. Now, these ideas will be clear once we move through the course a bit. But before that, let us discuss the main topic of our first class, that is black body radiation. So, black body radiation was the first topic or the first theory describing which the Planck came up with the idea of quantum. That's why I think it is important to all of us to know at least how this quantum idea developed regarding this black body radiation. So, first we have to know that what is a black body. So, let me just write here a bit and you can follow me. So, let me choose the color. Hmm. So, black body is a body that absorbs all the radiation of any lambda, where lambda is the wavelength of the radiation incident upon it. Okay, and it cannot reflect any radiation, cannot reflect anything. Okay, so just bear with my handwriting in Wacom for a little bit because I am doing this for the first time and the handwriting might not be the best. But I hope you can understand, and if you have confusion you can let me know. And anyways, I will just refer to the lecture notes that I have prepared, and I will attach them and send them through mail so that you can follow the detailed expressions later. Okay, so black body is basically a perfect absorber, alright. So it basically absorbs all the radiation that is incident upon it and cannot reflect anything. So the question might come that why it is black. So because the color we see in different objects is because of the wavelength it reflects from the surface, reflects the wavelength. So like say we can see that a flower is red, that means we are seeing the red color because it is actually reflecting the red colored wavelength from its surface. So from here we can know that since black bodies cannot reflect anything, absolutely anything from its surface, so all we when you look at its surface we see it black. So that's why it appears black to us, because it cannot reflect anything. Okay, now there's another thing that we can mention in this case, that since it is a perfect absorber, the absorption coefficient denoted by A is 1 for black body. So the absorption coefficient A is basically the energy absorbed by the surface divided by energy or the radiation that is incident on the surface. That means it's basically the ratio of how much energy gets absorbed of what energy that is total incident on the surface. So since black body absorbs absolutely total energy, so that's why we say that A is equal to 1 for a perfect black body. And later, if you know that we will not go into details, but there's this law called Kirchhoff's law, which helps us to know that if any body is a good absorber, then it will also be a good emitter, because the emissive power, uh, let's say I'll just give the expression and then I'll discuss. So this is the expression that we can achieve from Kirchhoff's law, that E2 by E1 equal to A2 by A1 equal to constant. So A2 and A1 basically of two bodies, 2 and 1, they are the absorption coefficients ratios of the two bodies, and E2 small e basically denotes the emittivity of any body. Emittivity is actually proportional to the emissive power or emissive efficiency of any body, like how much radiation it can emit from its surface. So basically from this formula we can see that they are actually linearly proportional to each other. So if A2 is greater than A1, that is body 2 is a better observer than body 1, then automatically E2 is also greater than E1. That means the body 2 will also be a better emitter than the body 1. So in this scenario we can say that black body is not only a perfect observer, is also a perfect emitter. That means it emits the radiation perfectly from its surface. Okay, now we have to mention that the perfect black body that we are talking about cannot be possible in reality, because it is a very ideal case and it is not possible in our practical world. But in practical world, what we can look at is examples which are almost very close to an or a very close approximation to a black body at least. So such examples, I have put some images for your reference here so that you can understand. So like the surface of sun or any star is actually a black body. Okay, and this black hole, you also know of black hole. You must have known of black hole. Is also considered as black body. I'll give you example why. Because black holes, you see, there the gravity is such strong and such dense is that anything absolutely that once enters into the black hole, let it be light also, it cannot escape when it enters into the black hole. So everything that is absorbed by the black hole, apparently it is perfectly absorbed. That means nothing is reflected back. So in that context, black hole can also be thought of a perfect absorber and therefore close to a black body. Similarly, these charcoals can also be an example of a black body or at least close to a black body. And the light bulb filament, where we see the radiation gives us the light, this filament can also be thought of a black body. So these are some of the common examples to give you some idea of what is a black body in real case. Now we just turn our focus into the black body radiation topic. So black body radiation. So what is black body radiation? So it is basically nothing but a thermal radiation. Okay, thermal radiation is basically, I will explain. Thermal radiation is when a body temperature, let's say T, is greater than absolute zero temperature. We know that absolute zero temperature is 0 Kelvin. So when a body's temperature is greater than its absolute zero temperature, then the body, what happens is that body emits radiation to its surroundings due to its internal thermal energy. Okay, so because of this radiation is called as thermal radiation. So now black body radiation is basically the thermal radiation for black body. Now the question might appear that why would we choose black body only? Like why not other bodies? What is so special about this black body radiation? So the answer is here that the universal spectra of black body radiation is what basically makes it so interesting and uh, like interesting to study, because you see for other materials also they have thermal radiation, but their radiation depends on their shape, size, composition, all these things actually controls the type of the thermal radiation for other bodies. Whereas for black bodies, the unique thing is that it its radiation spectra is completely independent of all these factors. Like they do not depend on the shape, size, or composition of the body, but the only thing it depends on is the temperature of the body. Temperature of the body. So basically, say if you have a bunch of black bodies, right, all of different shapes, size, and compositions, but all of them are in the same temperature T, then we can certainly say that all of them will have the same radiation spectra. So spectrum. So from here we can say that black body radiation has a universal nature, that we can think of a class of bodies which have this universal nature of radiation, and that's why scientists are mainly interested to look at this universal radiation character and it's the physics behind it. And another advantage lies in the fact that it is isotropic. That means whatever direction we are looking at, the radiation and the physics behind that remains just the same. Okay. Now, now we have already mentioned some of the famous examples of black body, but in laboratories, how can anyone make a very simple model of a black body? So this is the example of what a simple black body model should look like. So this is basically a cavity with a hole, with a small hole that connects it to the outside. So this can be close to a black body. How, I will explain. So let's say some radiation is actually entering this blue line. This blue line here is actually denoting the radiation that is incident inside the cavity from this hole. So the radiation is coming inside this cavity and it just reflects back and forth from the surfaces of the cavity walls. You can see here. But since this hole is such small a hole that once the radiation enters inside, it cannot just go back and reflect back outside. So this is not allowed. Not allowed means it is, even if it happens, it is very negligible in amount. That's why we are saying that it is not a perfect black body, but it is close to a black body at least, because whatever radiation is incident, as if all of that is absorbed within the cavity and nothing is reflecting outside. Okay, so that's why we can say that cavity with a hole is closer to a black body, and this is what is mostly used in laboratories to explain black bodies and its features. So we'll go into the details later, but let us first, for understanding the black body spectra, we have to know a few of the terms, a few of the standard terms that are important for that. So one is this spectral radiancy, this term, spectral radiancy. So the mathematical expression of this is RT nu. Okay, someone is joining. Okay, I've admitted. Okay, so we are discussing spectral radiancy, RT nu. So what is that? So it is basically the energy that is radiated from a black body. I am writing in short B body, black body surface at constant temperature T per unit area of the surface and per unit time. And in the, so nu is denoting the frequency. So in the frequency interval mu to nu plus d nu. So RT, so this is basically in short RT nu d nu. So nu is basically the frequency we are talking about, and d nu is the small range of frequency in the interval we are looking at, that is nu to nu plus d nu. So RT nu d nu, this product basically tells us how much energy is radiated from a black body from unit area of the surface per unit time and in the particular frequency interval nu to nu plus d nu. And remember that the temperature that is crucial at this point, the temperature for this case is constant to be T. So this is the expression. So this can be similar, this in simple ways, this in this spectral radiancy can be thought of like an intensity. So intensity, we almost are familiar from all branches of science that intensity can be something, some flow or something that radiation it can be that is emitted from, that is coming from unit surface area per unit time. Okay, so only here the temperature is crucial, that what temperature we are looking at and the frequency interval, because it is a function of frequency. Okay, now the black body spectra, here is an image taken from Google to show you what a black body spectra looks like. So you can see black body radiation spectra. Here y-axis is the intensity and x-axis is the wavelength lambda. So basically you see, we can, you don't have to be confused, because in some of the cases we will talk in wavelength space and some of the cases we will talk in terms of frequency, because nu equal to c times lambda, where c is the velocity of light, that is constant, we know, and wavelength of the light is lambda. Okay, and nu is the frequency. So basically since c is a constant, so nu can be just c by lambda. So nu is inversely proportional to lambda. So it does not matter whether we are describing the radiation in terms of wavelength or frequency, but we have to keep it in mind that both of these are inversely proportional to each other. So like in this diagram we are looking at in terms of wavelengths. So this is the black body radiation, the intensity or spectral radiancy versus wavelength for different temperature. You can see this is 300 Kelvin, 400, 500 and sorry 100, I am saying this is 1000, 3000, 4000, 5000 and 6000 Kelvin. Okay, so and there is a specific feature that can be seen from this graph. I'll explain it step by step, but before that, we can also look at the same graph, but here this is in frequency terms. We'll be mostly discussing in frequency terms also. Uh, Here we see that the spectral radiance RTNU in the y-axis, and it is plotted as a function of frequency in the x-axis. This is an experimental data that was taken in the year 1999 for the first time. This is a blackbody radiation spectra for different temperatures. Okay, so there are some important observations at this point that we have to look at from this radiation spectra. So let me go into that step by step. So the first one is, number one is that at any fixed temperature, let's say we are not looking at all the temperatures, we are seeing, let's say, for only 1000 Kelvin. So any fixed temperature, we see that this radiation intensity is initially almost zero at very low frequency values. And then as frequency rises, it also increases and reaches a peak here, okay, at this point. And then again it decreases and goes to zero again at very large frequency values. So we can denote it like in one line that RT nu actually goes to zero for nu tending to zero, that is small frequency values. RT nu also tends to zero for nu tending to infinity, that means very large frequency value. And in the middle, RT nu is maximum peak value it shows for nu equal to nu max. Okay, so this is not actually given in the or noted in the diagram here, but we denote this point as nu max 1. This is nu max 2 and this is nu max 3. So nu max is not nothing very serious. It's basically the nu max is the frequency or nu where the maximum intensity is obtained from the blackbody radiation spectrum, obtained as maximum. Okay, like you can see that for 1000 Kelvin, this nu max is denoted by nu max 1. This is here at this point, and for this 1500 Kelvin, this is nu max 2. This is a different value where the peak appears, and for apparently for 2000 Kelvin, it also shows a different nu max 3 value. Now, one thing that can be obtained just readily, that if you look closely into the graph, you can observe it readily that as temperature increases, like as we are going to higher and higher temperature, the blackbody radiation spectra actually shifts towards higher nu max values. Like you can see from here, right, that as we increasing the temperature 1000 to 1500 to then 2000, okay. So as the temperature is rising, the nu max values are actually shifting towards higher and higher frequencies. So as we are rising the temperature, the peak value where the peak value appears, that frequency is also increasing. And this is observed from the experimental data that this dependency on temperature is actually a linear one. That means the nu max is actually linearly proportional to the temperature. Or if we are saying in lambda or wavelength picture, then we'll see that lambda is inversely proportional to the temperature. Because in the last picture, you remember that this is in lambda space. So lambda is basically the inverse of frequency. So that's why the nature here is just the opposite of the later. But the physics remains the same. Like we see that as the temperature is rising from 3000 to 4000, 6000, the lambda maximum where the peak appears, this value and this value, you see this is shifting towards lower wavelength values. Okay, so this lambda maximum is clearly inversely proportional to the temperature, and this relation is actually known as a law called Wien's displacement law, which says that lambda max into T equal to constant. Okay, so this is the famous Wien's law. You remember I told you that I showed you a picture of Wien in that group photo. So this is a scientist, Wien, who proposed this law that lambda max should be inversely proportional to temperature, and this relation gives us a constant whose value is known to us, which is a standard value, that is 2.898 into 10 to the power minus 3 meter into Kelvin. Okay, let me just, yeah, the value is correct. And so this is the Wien's displacement law. Now we can clearly see a direct physical or practical example that this law is correct. Let's say we take an example of a iron rod. Okay, I suppose we all have seen iron rods or like say gas ovens, and have seen them heated in different temperatures. Like say if we take an iron rod and we just heat it up, we'll see that with change of temperature, as the temperature changes, so the color of the radiation that is seen from the rod also changes. So like initially when we heat up, the temperature is relatively lower, we'll see the flame that is observed, the radiation that is observed is a bright red flame. Then as the temperature rises, then the red changes to orange. Then as the temperature rises any further, then it becomes yellow. And finally, at very huge amount of temperature, very high temperature, the flame becomes blue white. Okay. So if you know the visible spectra, the Vibgyor lambda values, then we know that from red to blue, the wavelength lambda actually decreases. That means red has the maximum wavelength and blue has the minimum wavelength. Blue, not blue, but violet, but it is close to blue, let's say. So basically, we can directly see from here that as we increase the temperature, the radiation from the body, which is the iron rod for this case, actually shifts towards shorter wavelength. That's why we shift from the color red to the color blue white. So I think it is clear, I hope, that this is a direct physical consequence that we can see in our daily life, that how Wien's displacement law actually comes into picture. Now there's another important observation that is left to be made at this point. Let me just mention that. That is number 3. That is, we can see that as the temperature is rising, the area under the curves, that means if you look at the area under this curve, this portion, okay, so let me just dash this portion area under the curve for 1000 Kelvin, it's much smaller than the area under this whole curve, that is this, like from top to bottom, that is this 2000 Kelvin. So area under the curve in this case is actually denoting us a different term which is called as radiancy. We learnt about spectral radiancy RT nu, and for radiancy it is denoted by RT only. So what is radiancy? Radiancy is basically, mathematically, it is the frequency integral over the spectral radiancy. Okay. So like if we just take an integral over all the frequency ranges from 0 to infinity for the spectral radiancy value, then we can get the term called radiancy, which in normal terms will depict just the energy that is radiated from the black body at temperature T, radiated per unit time and per unit area, and in all frequency ranges. Like previously, for RT nu spectral radiancy, we are defining the frequency range from nu to nu plus d nu, but in this case we are taking all the frequency ranges from 0 to infinity. That's why we are taking the integral here. Alright, so this is the total energy radiated per unit time per unit area from the black body. Now why I am mentioning this is because if we look at here in this graph, then you see the integration, the area under the curve, that is the radiancy we have just mentioned, is actually increasing hugely as the temperature is rising. That means there is an empirical law describing this dependence on temperature of radiancy, which is basically RT equal to sigma times T to the power of 4. So it is dependent on fourth power of temperature. That means as temperature rises, RT, the radiancy or the power radiated per time per area, rises rapidly, which is in the fourth power of temperature. Okay, so this is the law followed by black body. So this is called Stephen's law. This is a very famous law, Stephen's law of radiation, where sigma is the Stephen-Boltzmann constant. This is also a standard constant value, like we said that lambda m into T equal to constant for Wien's law. Stephen's law is also well-known constant which has a particular value, that is 5.67 into 10 to the power minus 8 watt per meter square into Kelvin to the power of 4. Okay, so this depicts that how much the radiancy or how much the intensity is dependent on T to the power 4. That's why when we are increasing the temperature, the area under the curve or the power radiated is usually increasing. That is also known from common sense that if you increase the temperature, generally the radiation energy will be higher and higher, right? So these are some few of the important observations that are noted from this black body spectra. And now we just move into this we just move in the theory of black body radiation. So basically what we'll explain in this course is basically the quantum theory only. But for that for going to that, it is important that to know that there was a classical theory beforehand, which is given by Rayleigh and Jeans. These two scientists gave the classical theory of black body radiation initially, but it is important to note that the classical theory failed. Classical theory actually failed. Why failed? Because it did not match the experimental data as it was supposed to be. As we know that theory, the main motive of the theory is to match the experiments, right? So, but this classical theory that they both of them proposed did not properly match the experimental spectra of black body radiation. That's why the classical theory failed, and that's when scientists found that they need some other theory. They need some alternative theory needed for explaining such phenomena. That's where the relevance of this black body radiation arises. That from here the need of quantum theory, the a different theory other than the classical one appeared in scientists' mind. So basically, for just a brief preview, even if we are not discussing the classical one, so I will not go into the very details of the classical theory derivation, but I will provide you with my notes and the reference, and if you are interested, you can look into them from that. But I'll just go through the basic work process of this theory, how this developed, because this preview will be important when we'll explain the quantum theory ultimately. Okay, so like the picture here you see here is basically a cavity. Now we already said that black body radiation does not depend on the shape or size of the body, so that's why it does not matter whether we take a cubic shape or we take any other shape, does not matter. So for the ease of the calculation, we have assumed or people have assumed this cubic cavity which which is in 3D, this Ax, Y and Z, X, Y and Z. These three mutually perpendicular axes are drawn along the three edges of the cube. Okay. So and radiation, this all these lines are basically the electromagnetic radiation generated by the cavity radiation inside the cavity, which we have already stated that cavity radiation is similar to a black body radiation because it is close to a black body. Okay, so this is a model that we'll study to actually theoretically know the black body radiation physics. Now, uh, okay, so this is a cubic cavity, and the length of each of the edges of this cube is taken to be a. Okay, and now the important things that we need to learn from here is that the waves that we see inside the electromagnetic waves are basically standing waves. Now I do not know how many of you actually have a clear idea of standing waves, but I'll just discuss it briefly. The standing waves are some wave that cannot move in space, like it cannot move to right or left. Like in this case, they have two fixed ends. Two ends they are fixed. They cannot move beyond that. They can only oscillate in between this space with their amplitude oscillating in time. Like they cannot move from here or here because here are the fixed nodes of the wave. So that's why they are called standing waves. Okay. So here their nodes are nodal points. Basically, nodes are the points where the amplitude becomes zero for the wave. Okay. So like here there are two nodes at the two fixed ends. So this is called the fundamental frequency wave, that is denoted by uh, n equal to 1 and sorry uh, n equal to 1, and then there can be other higher harmonics also. They are also like standing waves, but in this case they have this extra node inside. This is for n equal to 2, and similarly we can have higher harmonics for like we can have more number of nodes, and then we can see this is for n equal to 3. So these are the basic idea of standing waves. Now we can have a picture over here that this is the two fixed ends at x equal to 0 and x equal to a, and this is the standing waves appearing. One is for n equal to 1 as we described, the other is for n equal to 2 that has one extra node, and other is for n equal to 3. Thus higher n values can also appear. Now why standing waves, or how does standing wave appear? It is because say we all any radiation inside this cavity, because it is in 3D, so we can break down the component into three perpendicular components. One is along x, other is along y, and the other is along z. So for simplicity, let us first only look at the x component of radiation inside this cavity. So I am drawing here the two walls at x equal to 0 plane and x equal to a plane. These are the two walls in this picture here. That is this for this case x equal to 0 wall is here, this wall, and sorry, this x equal to 0 wall is here, and this x equal to a, this wall is here. Okay, so for simplicity I am taking drawing them separately. So let's say this is the x equal to 0 and this is the x equal to a one, and they are absolutely parallel to each other, as we can easily see from the cube structure. So now whatever radiation is incident on x equal to 0 wall is actually reflected from it, right, like this. And the same radiation is also incident on x equal to a wall and also reflected from it. Now inside these two parallel walls we see there is a incident reflection radiation and there is a reflected radiation. Both of them are in opposite directions, but they have the same amplitude and same frequency. Okay, so we know that standing waves are formed because of superposition of two waves of the same amplitude and frequency moving in opposite direction. So that's why this incident and reflected EM waves inside gives us the standing waves inside the cavity. Okay, and these standing waves are actually have nodes on one of the surfaces. Like standing waves amplitude becomes 0 at x equal to 0 and x equal to a plane. Now these are also known from basic electromagnetic theory. I can explain you in detail if you have questions or if you have queries, but now let us for the time assume that okay, the standing waves have nodes on these boundaries x equal to 0 and x equal to a. So by similar assumptions, we can also look at in other directions, and we'll have the boundary conditions for this case, that whatever standing wave is generated inside the cavity will have nodes on x equal to 0 and x equal to a. Similarly for y equal to 0 and y equal to a, and z equal to 0 and z equal to a. Like these boundary conditions now put us some restrictions that not all frequency values can be allowed for the electromagnetic wave radiation inside the cavity, but there would be some allowed frequency values, like there will be some values which are not allowed and some values which are allowed. So we will not go into the detailed derivations of it, but the way Rayleigh and Jeans tried to solve this is they tried to find out the uh, density of radiation inside the cavity. So this is denoted by rho T nu d nu, which is basically the energy radiated from unit volume of the cavity, because density we see, so we take unit volume of the cavity. Now cavity's temperature should be at uniform temperature T, at temperature T, and in frequency range nu to nu plus d nu. Now the easiest way to find out this is that they just calculated from classical electromagnetic theory that what is the number of standing waves that are present inside the cavity in the frequency range of nu to d plus d nu. This term is denoted by n nu d nu. Okay, n nu d nu is the count of the standing wave that is present in the nu to nu plus d nu interval inside the cavity, and they multiplied it with the E bar, that is the average energy per standing wave, per wave, and the whole thing was divided by the volume of the cavity. So easily you can see that energy for each standing wave into the total number of standing waves present inside the cavity divided by the total volume of the cavity gives us the energy density radiated from the cavity. Okay, so now the calculations are a bit large, so I'll not. I'll again I'll give you the notes about that. And anyway, this is the classical theory, so we just don't need to like go into that much detail about that. So we'll just directly go into the final expression of n nu d nu, which is the count of standing waves inside the cavity in nu to nu plus d nu interval. This is 8 pi nu square by c cube into v into d nu. Okay, so don't bother if you cannot follow and write at the same time. I will provide you with the notes which have clearly mentioned all the required and relevant expressions. So this is the nu is the frequency, v is the volume of the cavity, which is aq for the cube, and c we already noted that it is the velocity of light. Okay, so this is the expression of the count of standing waves. This they calculated from the classical electromagnetic theory. Now the question appears for E bar. So by using the classical kinetic theory, they derived that E bar is equal to kT for each wave. So this is a theory. This formula. This comes from the classical equipartition theorem. That is also a classical formula, or classical concept, which is which will not go into the details, but you should have known the name. That the classical equipartition theorem says that for each particle and per degree of freedom, the average energy, total energy should be kT, k times t, and it is look at this is independent of frequency. This is independent of frequency nu. This is only dependent on temperature. Okay, so you can just clearly see that these are some diagrams that are relevant for the calculation, but I thought that they would be just too much like detailed and it will took too much time and deviate our concentration from the quantum idea, so I have skipped that. And you just know the final result that here the Rayleigh genes calculated from total classical idea that rho t nu d nu equal to n nu d nu, the count of standing waves, into the E bar, average energy per wave, divided by volume, gives as 8 pi nu square uh, into v by c cube d nu. This is the expression of n nu d nu we have derived, we have shown earlier. This by 1 by v, this cancels out, and E bar is taken as classically kT. So the final expression is uh, rho t nu d nu is equal to 8 pi nu square by c cube kT into d nu. Alright. So this is the classical Rayleigh-Jeans expression of the energy density. Now remember that we have earlier told about you about RT nu, the spectral density or intensity. So basically, clearly this density, energy density and the spectral radiancy are almost similar terms. Like rho T nu will be proportional to RT nu, because basically both of them are telling us the energy radiated from the black body surface. So they are always proportional to each other, and this is basically the formal form of Rayleigh-Jeans theory that is entirely classical. Now this theory was derived, but then what went wrong? Like if you can see in this diagram that this is the experimental result of blackbody radiation spectra of RT nu, the energy density versus the frequency, and this is the classical theory that was given by Rayleigh and Jeans. So this is for temperature T equal to 1500 Kelvin. Now you can clearly see that the theoretical expression they had given cannot fit the entire experimental data in the whole frequency range. Like you can see the very few or very narrow low frequency regime, nu tends to 0 regime, is actually closely matches with the experimental part, but other than that it actually diverges and goes to infinity, like rho t is going to infinity according to the classical derivation. Whereas in real case, experimental case, we see that rho t or radiancy cannot ever go to infinity or cannot diverge. It actually reaches a peak value and then it again decreases, and even it goes to zero. It goes to zero as rho tending to infinity. Okay, so clearly this shows us how badly the classical theory failed to explain the blackbody radiation spectra. Okay, this phenomena is called ultraviolet catastrophe, which is also a very important term. it is called like that because if we look in wavelength picture instead of frequency, since wavelength and frequency are inversely proportional, so just the nature alters. Like here in low frequency range it matches, but in wavelength case for high wavelength range, the theory and the experiment matches. So basically here the Planck is basically the Planck later quantum hypothesis, which basically exactly fit with the experiment. It is basically the experimental data, you can say, this dot. So you can see the lower wavelength regime, a whole entire regime in this lower wavelength, this to this almost. This actually does not match the experimental data into the classical theory. So, and ultraviolet is for lower wavelength. So that's why, since the discrepancy appears in lower wavelength or high frequency regime between classical and theory and experiment, that's why it is called ultraviolet catastrophe. Now, now our alternative theory was needed, which to explain all these phenomena. Now Planck thought that if we had to resolve this issue, then we need to think of the energy to be altered somehow. Like the average energy, it should it should be somewhat like that it should go to kT, which is the classical value that we have said earlier, at nu tends to 0 range, and also it should go to 0 at nu tends to infinity range, because you see that this spectral radiancy actually goes to 0 at nu tends to infinity. So if we have to follow this experimental result, then we have to have some energy that is actually going to 0 at larger frequency range. Now these two are the conditions to start off. Now for that, Planck proposed for the first time that all the problem is solved if we take energy to be discrete. Okay. So instead of the classical idea that energy can be continuous, that energy can take any values, Planck proposed that energy can be discrete. So he said that energy can come in terms like 0, delta E, 2 delta E, 3 delta E, etc. Okay. So where delta is nothing but the small packets of energy. Like we said that this energy is discrete, so energy is discrete by the small gaps. So this is a uniform gap maintained between the energy values. So, and the energies that are allowed are this 0 delta E, 2 delta E, all these integer multiples of delta E. Alright. So, this is the first like phenomenal proposition by Planck, that energy can be discrete, and that actually solves the whole problem. And another thing is important, that classical idea suggested that this average energy is kT, it is independent of frequency. Frequency has nowhere to play a role here. Okay, that is all actually not right, because we are seeing that how the spectral radius is itself changing itself with frequency. So if you somehow can implement some frequency dependence in the energy values, then it also solves our problem. That frequency dependent energy we have to obtain. So this was the idea of Planck that he started off with. Now for that, we'll just look at to understand the mathematics now. Since it is a quantum hypothesis, so we'll have a bit of a derivation here. But for that, just look at this probability distribution curve here. Nothing to be scared of. This is just a Boltzmann probability distribution, which is for a classical distribution, basically for distinguishable objects. Okay. So here we see the probability of a certain energy to appear, that is given as Pe, which is the probability of this energy E versus E is drawn. Okay. So this actually shows that as energy increases, this probability function drops, and the standard form is well-known form of probability distribution of Boltzmann is e to the power minus E by kt. K, all this while I am using this term K, I forgot to mention that K is just the Boltzmann constant. It is also very well-known and standard constant. That's why people always mention it by K and don't need to explain once they say K, because this value is also fixed, minus 3 joule per Kelvin. Okay, so now this is a standard form of Boltzmann distribution. You can just take this term to be true, and then we will just look at this curve. So this is the experimental plot of this expression, and the average energy classically, if you look at, it is explained, it is derived by this way, like the energy integral, weighted energy integral for E divided by the total. So once we know the probability distribution of a certain quantity like E here, we can calculate its average value by just taking a weighted average. Like we take the weighted average of E here in the total energy range of 0 to infinity, and we normalize that by the total probability, which is anyway going to be 1. We know the total probability of any case will be 1. So basically we are left off with E bar equal to 0 to infinity E PE dE integral. Now this is the classical idea of average energy. Now looking at this classical idea, we can show that this is, we actually mentioned that if we take a graph of E into P versus E, then the area under the graph, like this graph here, area under the graph will actually give us the value of E bar. Because you see that this area is basically, actually we are integrating the total energy range from 0 to infinity of this function E times P. So basically, E bar gives us the energy, that is the area under the curve, energy not energy, yeah, the average energy, that is the area under the curve here. And this is the classical continuum case where the average energy is calculated to be kT, like we have said earlier. But now had gone into discrete energy limit. Like he proposed that energy are not continuous, energy comes in 0, delta E, 2 delta E, these gaps. So this is the classical continuum dotted line, and this is the Planck's discrete quantum energy levels drawn here. Like you see 0 after that delta E, then 2 delta E, thus the energy levels go. So this is discrete case, that's why we see these small rectangles out here instead of a continuous line. So you see here when this delta nu is very very small, right? It is almost very very small than kT. That means kT is our working energy value in this case. So if delta E is very very smaller than the working energy value, then absolutely the gap between the allowed values is that small that it seems almost continuous. Like even if it's discrete, like it is a common example, right? If you take very very large gap distance, if we place these sticks in very large distances, then you will see that they will appear to be discrete. But when you just place these sticks very very closer to each other, all right, so then delta E is so small, so small, almost tends to 0. That means it is almost looking like a continuum case, like in this case. So it does not make any difference. It always gives us almost similar to a classical result where E bar is nearly equal to kT again, because the delta is very very small value than kT. This is the case 1. Case 1. Okay. And this is the case 2 when we just slightly increase the delta E ordered value. Let's say this is not any more very very smaller than kT, but this is in the order of kT. So that means it is a significant large value for us to show the, like to see the energy values to be very properly discrete. So then we see that 0, this is again after the delta E, after a large gap is appearing, and then this is 2 delta E, then 3 delta E. So here we say that because the gap and discreteness has been increased, so the results changed very much from the classical result. Like the average energy in this case is not kT anymore, but it will be smaller than kT, because you see that the equal to 0 takes up a larger contribution. So that's why the average energy here decreases from the previous one. And now this is case 2, and finally this is the case 3, which is the most important and distinctive case, where we see the delta E's value is taken to be such large that delta is almost very very greater than kT we are seeing. So you see kT is appearing here after 0, and delta E is where? Delta is after so much distance. So this is such larger than kT, this is our working energy range, so that the values are almost discrete, and we can only see the contribution from E equal to 0 mostly. Otherwise, in this space, these are empty. No energy levels are allowed here. Okay, no allowed energy levels here. So what happens? Basically, most of the contribution in this area under the curve comes from equal to 0. That's why the average energy becomes much smaller than kT. This is the third and final case. Even it becomes such smaller that you see the small arrow here. Small arrow here. I will just erase this part. Small arrow here you can see is actually depicts where the E bar is lying. E bar is actually very very close to 0. Okay, for delta E much greater than kT. That means the gap between the energies is very very small, making it very very discrete. So you can see here Planck's intention has been satisfied. Like he has solved the trick. Like if you take the energy gap to be very much large, then you can get average energy closer to 0. That's what we need for nu tends to infinity, right? For nu tends to infinity, we said that we need to have where did I left that? Okay, whatever. I will just write another for one more time. Nu tends to infinity from the observation. We said that for to match the experiment, nu tends epsilon should be 0, and for nu tends to 0 to match the experiments, the epsilon should be uh, nearly equal to kBt, because that's where the classical result matches with the experiment. Now, Planck has solved this problem. Like if he said, if we take the energy levels to be such discrete, like delta E is so large that then we say that E bar tends to 0 almost. And if we take the energy values to be almost continuous, that is delta E is a very very small value, then it is almost giving us a classical result. Now we can immediately connect the delta E range with frequency. Like for frequency tending to 0, we also need delta E very very small, right? Almost 0. And for frequency tending to infinity, we also need delta E very very large. That means delta E has a direct proportionality with this frequency. This is the gist of all these calculations. Like delta E has to be linearly, the most fundamental form that Planck has proposed for that time, the relation should be directly proportional, that delta E is equal to h times mu. Now, because of the proportionality, the h is the proportionality constant, which was later numerically calculated and known as Planck's constant. This is also another universal constant and very, very important for quantum idea. This value is fixed to be 6.63 into 10 to the power minus 34 joule second. Okay, this is the universal constant. Nu is the frequency of vibration of the waves, and delta E is the energy, discrete energy packets or discrete gap between the energies. So this was the first statement, that energy was discretized, and if the energy was discretized, then the theory can actually exactly match the experiment. Look how surprising or how amazing does it look to see how a theory evolved from a scientist's mind, that he actually thought of such a trick that if he could like process these terms in such a way, then he could easily get his theory to exactly match with the experiment. Here these data points are experimental data points of blackbody radiation, and this line fit is actually coming from Planck's formula using the quantum theory. Okay, now the ultraviolet catastrophe that appeared earlier for classical theory is gone, and this is we see an exact fit to the Planck's quantum theory to the experimental data. Now here I will explain. Here I will explain the. Let me take a new page uh, because I will moving into a derivation of this quantum theory. So I'll just quantum theory derivation of Planck. Don't worry, this will not be very tough derivation. This is a very logical one. You will understand once I do it. Okay. So what Planck did, remember that delta E he proposed to be h nu, and he also proposed that energy allowed value should be 0 delta E, 2 delta E, like that. Okay. So that means if delta E is equal to h nu, so the allowed energy value should be 0 h nu, 2 h nu, 3 h nu, dot dot. So in short, E should be in h nu. That means the allowed energy levels are actually integer multiples of h nu value, where n can be 0, 1, 2, these integers. Later we'll see that this n actually depicts the quantum state of any matter. So these integer values actually depicts the quantum state. H is the universal Planck's constant, E is the allowed energy values, and nu is the frequency of oscillation of the black body radiator. Okay. So with this idea, we say now see, for classical the idea was continuous, and for quantum the idea has been discrete. So the classical, for calculating E bar, we used to do integral like 0 to infinity E P d by 0 to infinity P d, right? This was E bar expression. But for quantum, because this is discrete, so the integral will be converted into summation. Simply this is a common idea, because it is discrete, it will not be integral, it will be a summation. So here E bar will be for summation over n equal to 0 to infinity E P divided by n equal to summation 0 to infinity P. Okay. where E equal to NH. Now we'll derive the expression of E bar for this derivation for applying this quantum summation idea. Okay, so just go through the process with me. Okay, we put first the E value in this equation, that is NH. And PE also already said that this is the Boltzmann probability, which is e to the power minus E by KT by KT. This is the known form. So this E is replaced by NH2 in here also. That means it becomes NH nu by KT divided by KT. Alright. And here it becomes N equal to 0 to infinity e to the power minus NH nu by KT divided by KT. Okay. So we have just written down the terms in terms of NH. We have replaced E equal to NH here. Now, for simplicity of calculation, let us take this H nu by KT, denote it as alpha, because it looks too much larger terms in calculation. So we denote it simply by alpha. So it becomes, say, this is H nu, this is KT, so H nu by KT in alpha, and e to the power of minus again in alpha. Alright, and this is sum over n equal to 0 to infinity. This kt, this was in bottom denominator, so this comes up, this kt becomes in the numerator, and this is again e to the power of, sorry, I forgot the minus, so this is e to the power minus n alpha. So up to this I think it is clear. And then to solve this looks like a complicated term, but to solve this we have an idea. Like, we'll use another term. Let's say, let's forget about up to this part, then we start it here. That take minus alpha dd alpha of ln, okay, ln n equal to 0 to infinity to the power of minus n. Let's say we are taking a derivative of this term with respect to alpha. Okay, so what will be the derivative? So derivative will be, since it is ln, so it first comes in the denominator as 1 by x type of form to the power minus n alpha, and then in the numerator we see it becomes dd alpha, so we have to take the derivative. That means it is minus n sum over, sorry, sum terms always comes first, so sum minus n, alpha was already there, so we take the alpha inside and to the power of minus n alpha. Okay, so writing it clearly, so this becomes n equal to 0 to infinity. Now this minus as this minus cancels out, so it becomes n alpha to the power minus n alpha, and in the denominator it is already equal to 0 to infinity to the power minus n alpha. Now look at the striking similarity between these two forms. Okay, this is also the same form, and this same form is obtained here apart from the kt term. Up to this term is similar. So what we'll do, we just replace, because these two values are similar, so we just replace this value into this equation. This is for the simplicity of the calculation. Like, this is how it is solved. So we say this E bar equal to kt into, we replace here this term minus alpha dd alpha ln of sum over n equal to 0 to infinity to the power of minus n. Okay. So since alpha equal to h nu by kt, okay, I think I am just a little exceeded from the class time, but it's actually initially we started a little late also. Just give me 5 or 10 minutes more and I will be finished. So here uh, this alpha is h nu by kt, so this term cancelled out and it gives us h nu. Okay. And this is k del alpha, again ln of sum equal to n equal to 0 to infinity to the power minus n alpha. Now here we can expand this in a series expansion. Like, for writing in more simplified terms, we write this n equal to eta, n equal to e to the power minus n alpha, where depending on the values of n, this can be e to the power 0 plus e to the power minus alpha plus e to the power minus 2 alpha plus dot dot dot, equal to 1 plus x square plus dot dot. If we can take x equal to e to the power minus alpha, then we can reduce the series into this. So basically this is a familiar form. This is an infinite series which value we know to be 1 by 1 minus x, that is 1 minus x to the power minus 1. Now this is x equal to e to the power minus alpha, so it becomes 1 minus e to the power minus alpha to the power minus 1. Now we just replace this term into this part. Okay. So what we will do is we replace E bar equal to minus h nu and minus del alpha of ln, right? So minus del alpha ln of 1 minus to the power minus alpha to the power minus 1. Now we again have to take a derivative. Now this time it is a bit simpler because minus n h nu comes out and this is just again ln, so 1 minus to the power minus alpha to the power minus 1, and again we take a derivative on that, so it gives us minus 1, 1 minus to the power minus alpha to the power minus 2, and then derivative over this gives us 0 minus 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 plus to the power minus alpha. So this basically equal to h nu. Simplifying, this cancels out and this leaves us with e to the power minus alpha divided by 1 minus e to the power minus alpha. Now this again it becomes, if e to the power minus alpha, if we cancel top and bottom, then it becomes e to the power alpha minus 1, which is precisely h nu by e to the power of h nu by kt minus 1, because we said that alpha equal to h nu by kt. Now uh, okay, yeah. So this is the final expression that was derived from Planck's hypothesis of quantum idea of average energy per standing wave, that E bar equal to h nu by to the power h nu by kt minus 1. Now the interesting thing that we can immediately see from this expression, that average energy per standing wave. Okay, you can see the limits Planck tried to achieve are already been achieved in this form, because if we take nu tends to 0 in this expression, then by binomial form e to the h nu by kt is also tending to 0, then it is very small. Then by binomial expression we know that e to the power x is nearly equal to 1 by 1 plus x if x is very smaller than 0 or tends to 0. Here take x at as h nu by kt. Then for nu tending to 0, this term reduces to h nu by 1 plus h nu by kt. This comes from binomial expansion here and this minus 1 here. So this minus 1 plus 1 cancels and this just becomes kt. So you see that E bar just has become kt like the classical result as before for nu tending to 0 as we want, because in nu tends to 0 limit the classical result actually so explain the experimental data. Okay. Whereas for nu tending to infinity, that was the problem in classical case. In this case, what happens is that for nu tending to infinity, h nu by kt also tends to infinity, and e to the power of h nu by kt, that means e to the power infinity, goes to infinity. That this you know, and 1 by infinity tends to 0. This is also known to us. That's why for nu tends to infinity, what happens is E bar tending to 1 by infinity tending to 0. So these are the two precise limits that Planck started off with, that he has to reach for nu tending to infinity, E bar tends to 0. And for nu tends to 0, it is already satisfying the classical result, that is E bar equal to kt for nu tends to 0. Okay, so the problem is solved. The new E bar actually explains the classic experimental data so well, and therefore the final take home message or the summary, take home message or the summary that we can take from this after all this derivation of Planck's quantum hypothesis, okay, that the energy is actually discrete. Energy cannot be continuous like classical case. Like for classical, if this is the ground state equal to 0, so the energies can take any value. This zigzag lines I am drawing is basically to denote that energy can be a continuum value. Like it can take any value possible, and this is for the classical case. Okay. But in quantum case, which was proposed by Planck, that energy cannot just take any value. This is, if this is the ground state equal to 0, then energy actually comes in regular intervals, in discrete allowed values. Like this is 0, after that this is h nu, this is 2h nu, this is 3h nu, and order integer multiples of h nu, because the distance between this wave, this allowed values is uniform, and this is dependent on the frequency of vibration, that is nu. So Planck proposed, that is the main idea, the main statement of Planck's hypothesis is that any entity that's oscillating in time, that's oscillating, will have discrete allowed energy values given by equal to nh nu. That the first very first block we actually explained during the revision of quantum history is equal to nh nu given by Planck, where n can be any integer from 0, 1, 2, 3, etc. And nu is the frequency of oscillation of the entity, and E is the allowed energy values, and n is the quantum state that is noted by in these integers, and also h is the universal Planck's constant. So this was the brief message from this class, that Planck actually stated that statement of energy to be discrete, and he actually resolved the discrepancy of the blackbody radiation experimental spectra from the theoretical result. Okay, so this is the relevance of the Planck's theory, and later on we'll see that later on Einstein actually improved and developed on this theory even further, and in the next class we'll see his invention or his explanation on photoelectric effect, and which actually later confirmed that not only any oscillating particle in blackbody radiator, but for any mechanical oscillators, like anything that is oscillating in simple harmonic motion, can have such energy levels discretized like nh nu. And it also described later that light or radiation, this is the most crucial statement, that light or radiation which are supposed to be wave, supposing to be a wave in nature, earlier in classical physics idea, can also have particle-like properties. Why particle-like? Because we have seen that the uh, energy is discretized. Energy comes in discrete wave discrete energy packets. Like energy comes in this h nu packets and goes into the integer multiple of that. So this was not even thought earlier. Light was always thought of as a wave nature, but then quantum idea evolved, and it stated that light which seemed wave in nature, can also have a particle-like property. So from here we will start from our next class, that how the particle property was introduced in the light or wave nature, and this is the end of today's lecture, that Planck's blackbody radiation and quantum argument. Okay, so now I just stop sharing, and I will ask if any of you has any question or doubt that we need to discuss in this lecture. Okay, let me just go through the chats. Please share notes. Okay, yeah, I will share the notes right after the class. I will also refer to the book. I have mainly followed Iceberg Presley Quantum Physics for for this part, and I'll follow the book reference. I can share you the PDF also. But before that, can you we can have a little discussion, if you can, if you have any doubt regarding today's class, you can just ask and I'll try to explain. Okay, so any of you have any question, like anything you that was unclear during the lecture session? Okay, I'll wait until 5, and if nobody has any question, then I suppose that this will be the end of this class. And if you have questions, you can email me also. I'll try to answer them in the class. But it will be best to interact directly in the class only. So um, and yeah, you will get the notes and references from the emails. And this lecture is also being recorded, so if you can access any point, you can get the recording. Okay, so people are leaving. I think anybody, if you have questions, just feel free to ask. We are all students. Like I am myself a student. He is a student. Just so we'll just learn from each other and try to learn the things. So I'll try and explain try to explain by my best if I can clear your doubt. Okay. Okay, I'll just wait until 5, and then if nobody has a question, then I'll just stop the class. Yeah.
Hello, Sugata.
Yeah. Hi. Hi.
Yeah. See, I have one query. See,
Yeah.
after this ultraviolet catastrophe,
Yeah.
where the Siri has failed in the UV region,
Yeah.
what made them to think of that the, the equipartition energy, which is KT,
Hmm.
is not the right term? But what made them to think of the discreteness, like zero delta E to delta E?
Yeah. Yeah. I'll explain. Just let us again go to the notes one so that I can refer to the graph. Hmm. Where is ultraviolet? Okay, this one. So you see that for the classical theory, the problem with it was that the average energy kT was not dependent on frequency only, right? So it was just a temperature dependent quantity, E bar equal to kT. So that's what what main requirement we had in this case was that we should have an energy that is changing with frequency in a way that it actually satisfies this car. All right. So like we need to have at nu tends to 0, we need to have an energy that actually goes like a classical one, because here the two curves match. So at nu tends to 0, the classical result was fine. Okay. But as nu going to infinity and larger values, then we see the classical theory actually like diverging the quantity, because its energy E bar does not have any frequency dependence, no frequency dependence. Okay. So in this point, Planck thought that if he could introduce some frequency dependence inside this energy, average energy component, in such a way that these two limits are satisfied. That means nu tends to 0, the energy would be similar to a classical one. But for nu tends to infinity, the energy will be decaying to 0, like this distribution curve decay. That's what the main idea in Planck's mind, I suppose, when he first came to think of this theory. And also because the classical theory failed, so he knew that this continuum energy cannot probably work. If we have to resolve this issue, we should have thought of a process like discrete energy level delta E. And I have also explained from these cards also, this case 1, case 2 and case 3, where we can clearly see that taking different delta E values in different limits, we can actually move from classical to quantum results. Like for delta E, if we take very small delta E, like the gap is so small between both energy levels that we can almost not see them, like it almost seem as continuous. So in that case, for small delta E, we saw that we can retain the classical result that we need for nu tends to 0 case. Okay. But if we just take a larger energy gap, that means the energy gap is so huge that we can clearly see that they are discrete energy levels, that is equal to 0, that is equal to h nu, that is equal to. So in that case, it actually helped that in this case for nu tends to infinity, this average energy becomes so small that it actually came very near to 0. That our purpose solved, that nu tends to 0, E actually going to 0. So am I able to explain to you that how this actually all this theory connected, or because it's all about the frequency dependence and the limit that is taken for uh, delta E, that actually helped to match the theory with experimental data. Is it clear, or
Yeah, yeah, fine. I'll mail you my doubt here.
okay? So what point are you in confusion? Can you just
Like the scientists have rethought of
hmm,
taking this delta E
hmm,
uh, like frequency dependent,
yeah,
and they have come they have straight away introduced into some. But like, what made them to think of that? Like, there are some uh, blur points in the graph. Like if it is the average energy is very greater than KT,
Yeah.
Then there is a rectangular box at the end, which is like allowed energy state.
Yeah. That is a
Uh,
discrete level. So because you see that when the gap is so much larger, then after e equal to 0, the next line equal to h nu is coming so much away from the equal to 0 that almost most of the contribution is coming from equal to 0 only in the average. Like say we are averaging a lot of quantities, right? And some of the quantities like say smaller values have larger contribution, then what do you expect that the average value will be something closer to the smaller value. Like say in a class of students, if the students are giving obtaining different marks from, let's say, in the scale of 1 to 100, and if the number of students obtaining marks lower than 30 or 20 is larger, then we expect that the average energy of average number of the whole class marks of the whole class will be a small value, all right. So that's what the
yes.
same thing is happening here. Like if the energy levels are so much discrete that the one energy level from equal to 0 after that equal to h nu is appearing very far away from each other, then in the distribution curve most of the contribution is coming from the lower values, that means equal to 0. So naturally the average energy that used to appear at E bar equal to kT in earlier times for classical case, now it will appear at a very small average value, and such small that it will almost be closer to 0. That was a third graph, and if that is closer to 0, then we see that the energy density is actually the multiplication of the average energy times the count of the standing waves. So if the average energy is going to 0 at larger frequency limit, then we can also say that the energy density is also going to 0. That's why the graph, I think I should again, uh, this
Yeah, yeah,
graph.
got it, got
That's why the graph is also going to 0 at higher frequency values. You see, higher frequency or lambda, whatever terms we think of it. So if you are still unclear, I think I'll send
Yeah,
you
you
my,
share the notes, then I'll go through it.
yeah.
If I have any doubt, I'll ask.
Yeah, you can ask me in the next class. Also, you can mail me also, but I think it is preferable to like interact one because in mails I am not sure how much I am
Correct,
explaining or how much
correct.
you will get it. So yeah, that's so any further question from anyone, or else we'll just wrap up the class here and we'll have the next class on same time next Friday. But please, guys, please try to be on time. Like 3:30 is the time for the class. It's actually basically a 1 hour class, and if we have doubts and discussion, then we can extend it to 1.5 hours maybe. But please, like it is comfortable when all of you are joined in the proper time.